So the other application for water-related mapping using remote sensing is water surface temperature. So as you can see in this map over here, so the color over here, so a lot of time we can see from NOAA data set, we can see like global wide sea surface temperature and also land surface temperature. So this is one of the application of using the thermal infrared sensor to sense both the temperature on the water surface and land area. So because for example, we often, we may be able to obtain the temperature of inland water bodies and sea surface temperature during daylight hours and at night using thermal infrared remote sensing techniques. Because at nighttime, sunlight may not be there, but the different land cover, they absorb energy in the daytime and then release it in the form of heat. So the thermal infrared sensor will able to be sensitive to those temperatures. So you can still map them at nighttime. And these are other example about sea surface temperature mapping for the Atlantic Ocean. So you can see this kind of color transition from deep ocean to the edge of the land. And also this is example application of this temperature mapping to illustrate El Niño and this kind of global weather phenomenon. Okay, so you can vividly observe this kind of effect. Once you're able to map from certain time, then you can build model to show the dynamics. Like often you will see online, there are a lot of pictures showing the dynamic switch of these kind of NDVI and also temperature change. So you can see all year round how they change. And the other application is to map the precipitation. So as we know that water have significant absorption in the near infrared and thermal infrared area. So precipitation is basically water droplet in the air. So we can also use LiDAR sensor, the remote sensing certain channel to monitor the precipitation, because that's a big indication about where they or when there may be rain. So for weather forecast is very useful. So precipitation may be measured operationally on a local or regional basis using ground-based active microwave remote sensing. So notice here, the sensor that they use to monitor that is microwave remote sensing. So a lot of time when we look at this application in different area, let's pay attention to what kind of spectral bands that they pick. In this case, it's a microwave. So for example, the most well-known next generation radar system. So basically this is the one that they set just to keep monitor the area in the United States. So this is what we're actually providing the data set that we often see in the weather channel. Okay, so talking about this, I will strongly suggest you to download and use the app called My Radar. How many of you have ever tried the app? Oh, okay. Okay, yeah. So I get to know this app because sometimes we go to, for the coastal field trips. And one time I see one of our other collaborators have this weather is important for our field trip and, checking weather and other things to pick the suitable weather condition. And then they have this kind of app installed. And what's unique about it, they can show those detected clouds movement. So a lot of time when you have storm surge or hurricane that is coming, you can clearly see those formation of those clouds. And they will show you dynamic of several hours time, maybe 2 hours time, how they change. So even in the normal time, when there are severe events like that, I often open this app so that I can see how far we are, how far like Baton Rouge here, and this is coming by. So I can tell, I have better idea about when it may come and how long it may last. So this is a really useful app for Louisiana, since here we often have storm warning or tornado or hurricane. So in time like that, it will be really useful. And this is also another example showing the weather radar system. So these are a couple of, the cross here are a couple of stations distribution. So they show different kind of weather station that they can use to compose a data set. And this is one of the results showing where the clouds that may have heavy precipitation. So that's the weather radar sensor. And also, in order to detect precipitation, we often use, one of the common band we use is visible infrared techniques, because the brightness of reflected sunlight in the red and near infrared wavelengths from clouds might give an indication of their thickness and thus their likelihood of bearing rain. So a lot of time clouds may sometimes maybe having maybe white or sometimes darker color, but heavy precipitation will cause significant absorption especially in infrared. So that contrast, the one is in color, the other one is heavy absorption if they have water in the clouds, and that information can be helpful. So that's why they use both, one like in the invisible band, which is red, and one in the near infrared. So it's called visible infrared techniques. So the temperature, so these will be able to separate those bright clouds, but without precipitation, or clouds, but with a heavy precipitation that can form a rain. And also they can see the temperature of the top of clouds that can be used to estimate precipitation. Typically, the colder the cloud top, the greater the likelihood of precipitation. So these also indicate that temperature can have play a very significant role in precipitation. So, however, not all cold cloud tops produce precipitation. This means that when you try to use those kind of data sets to extract it, there may be a confusion between those cold clouds with heavy precipitation versus cold clouds that do not produce much of precipitation. Okay, so that's and then so another example is to use these GOES. So GOES is the weather system that use the two satellites to observe the basically targeting the United States to monitor the weather. So a GOES precipitation index based on analysis of thermal infrared. So they were using the thermal infrared channel band to produce that information. And they found that they can classify pixels as raining at the rate of 3 mm per hour if the cloud top temperature was less than 235 K. So these basically indicate that when you calculate, you can use those data set to produce the GPI index. And from this index, you can classify it you can use it to identify those with possible will produce rain. And then also, they provide twice daily estimate of outgoing long wave radiation from polar orbiting infrared sensors on board this AV-HRR sensor to estimate monthly rainfall. Okay. And this is one application by for Hurricane Floyd in 1999. So as you can see that you can clearly see the formation of this significant event, and based on the location in relative to your city, it can be very helpful for those people who want to watch the event or want to plan whether they should evacuate or they should stay. So this is one of the applications to map these kind of severe events. And we can also measure precipitation through microwave technique. So the theory is that those precipitation size, kind of relative larger size, ice particles and large raindrops in the clouds will significantly reduce the emissivity of the clouds and thus depress its brightness temperature to below a normal background level. So this means that because of that, so your temperature, so you have like, so your temperature will drop because of that heavy precipitation. So these will allow rainfall level to be computed. So one of the examples to use the first special sensor microwave imager, SSM /1I. So this is launched in 1987, and they have a high frequency channel of 85.5 GHz. So that's basically indicating of these microwave channel that they use. And they have 15 by 15 km spatial resolution. So basically, most of the weather sensor have much coarser resolution because they are not looking at like cover types and others, and usually looking at a weather phenomenon in much larger scale. So this is also the one that often provide worldwide precipitation estimate. Often can be used for the modeling of the global weather application. And the other data resource is the Tropical Rainfall Measurement Mission, which is TRMM. So on this mission, they have microwave imager, which is TMI, and then precipitation radar, PR, and visible infrared, so, and also lightning imaging sensor, okay? So these are the 4 sensors. You can see that it's mostly based on for weather applications. In this example, it shows the tropical rainfall measurement mission, like TRMM imagery on March 9th, 1998. So as you can see that using this kind of very coarse resolution sensor, they were able to map the global distribution of clouds distribution in just 1 day. Although there are some gaps over here as you see there, but it kind of gives idea about how this weather phenomenon goes in this area. And then this is another example showing that from this TRMM data, they were able to map this tropical cyclone Mageda when it was off Australia. So basically the point is here is that the message here is that they were able to map this kind of 3D map for it. So the vertical over here, I think it might indicate wind speed, or it looks like a wind speed for me, but you can check the website for more detailed information. But anyway, so a lot of time when we do application, being able to see and map it in a 2-dimensional versus be able to measure the 3rd dimension in certain aspect is important progress. Okay. And then the other one is to map the clouds in visible image. For example, the ghost sensor. So if you want to know the detail, you can pick it up, but I think we talk about it in this class. So again, those are the 2 weather sensor that is monitoring the United States. So it was first launched in 1998, and they have visible band, so it's basically 3 channels, and then plus the thermal infrared for clouds. So notice that the choice of the band. And then they were able to monitor frontal system, intensive thunderstorm activity associated with tornadoes and hurricanes. Okay. So these will be, I think this is the main resource when the weather report used clouds movement. So this is an example of this data set that used goes west because they have 2 sensors. So from the west sensor, this is how the visible channel, how it looked like. And this is the east satellite, how it look like in the visible channel. And then this is how the thermal infrared look like. So as you can see that those significant weather event were able to capture by observing this cloud movement. And the last one over here is the channel about water vapor. So you can see that the main difference between, for example, thermal infrared and this one over here, the bottom one, they appear to be much more sensitive to the subtle water vapor content in the air. Okay. And then we can also map clouds in visible imagery, because a lot of time clouds may appear to be white, or like, for example, often we see clouds in Landsat image, so they present quite a different color in comparison to other ones. So there will be application in this visible band to map the clouds. So one of the example is the METEO SAT, which is the weather sensor used by the Europe. So it's a geostationary meteorological satellite located at 0 of latitude and longitude. So again, the GOES system in the United States is also a true geostationary sensor. You still remember what's the definition of geostationary? It means that it kind of fixed in the relative location to the Earth. So when the Earth is rotated, like the sensor is moving at the same pace, but from the ground, it appears to be the stationary above certain locations, okay? So that's the meaning of the geostationary. So a lot of weather sensors like this were actually geostationary. So let's take a look at what kind of band they use in here. So visible band, because a lot of the time clouds appear white, quite bright. So that's very helpful for us to detect clouds. And then thermal infrared, temperature play a big role, and also the water droplet we're going to absorb, and then that also causes like separation, that you can help separate those with or without precipitation. And also those the water vapor. So basically this is the spectrum range that is sensitive to water vapor in the atmosphere. Okay, so they have one visible band, one thermal infrared, and one water vapor band. Okay, so this data set is transmitted every 30 minutes. Okay. The other one example is the DMSP, Defense Meteorological Satellite Program, and they use the visible imagery at nighttime, and the use a light sensitive instrument, because at nighttime, if you're able to map these kind of, you need to be sensitive to that. So this is the example image of what they derive from the sensor. And then we can also use thermal infrared image to study clouds. So the thermal infrared band that used are commonly range between 10 to 12.5 UM. So usually it's available at nighttime, and also of course that is for 20-hour monitoring. It's usually for weather, so they put it 24-hour monitoring. In satellite meteorology, infrared imagery are normally inverted, i.e. the greater the radiance a pixel, the darker the pixel, okay? So the greater the radiance a pixel, the darker. Let me think about it. So the greater the radiance, meaning more reflectance, so less absorption, and then they mark it as darker pixels. Yeah, I think this is the way that they want to, using a white color, like bright color, because they are mapping clouds. So they want to highlight clouds. So those clouds, they want to use that to, reserve the brighter color for clouds. I think that's why they kind of reversed it. Okay. So this is the example from GOES. This is the first infrared image from newest weather satellite captured Hurricane Bill in 2009. So basically here, this is the Hurricane Bill, and there are several other ones that is observable in the image. So as you can see that this kind of sensor is quite useful for detecting this kind of severe event.
So these geostationary satellites, with like the angle that they record data, like that affect how accurate it is. So like
from the weather sensor, they typically have a lot of distortion because it's geostationary.
Yeah.
But a lot of time, people in this kind of application, they are not taking statistics of the area or location, so they have less concern about that part. So yeah.
So how are these satellites located above the cloud?
You like, for example, the main one, the GOES satellite used in the United States. So they geostationary in 2 of the locations, and that covers the United States.
They are all above the cloud.
Typically, yeah, it's like satellite should be above clouds.
Okay, but for the multi-sector satellites, they're normal Landsats. They're not normal.
Usually, most of the satellites should be above the flight height, okay, you know, to avoid the traffic issue.
Yeah, I'm just trying to imagine, like, for multi-spectral images, the normal one, like, are they cloud sensitive? Because if they images above the clouds, maybe the clouds will blow it.
Yeah, they are cloud sensitive because, like, in the visual band, they want to see the white cloud, because when cloud appear to be white, it contrasts with the surrounding environment. So that's how they can identify the cloud movement, you know, the event movement. Yeah, they actually want to see the cloud. So yeah. So let's take a look at another special application. In this case, you will see example to determine cloud type. So a lot of time when we talk about different application, we want to cover different type of application. So in this case, not only they can detect where the clouds are, but they try to identify, you know, sometimes the density difference and others. So in this case, let's see what they be able to separate. For example, they will say, okay, this is the sea, and this is the land area, and some type of clouds and mid-level clouds, and so these kind of clouds that will relate to the weather-related knowledge that expert in this field can further use this to derive more accurate information. But the message over here is that it is possible for them to further discriminate the cloud type using these visible and thermal infrared. So a lot of time there are various algorithms available, and typically temperature threshold may be involved in this kind of process. So for those students who study climate or hurricane event and other things, these type of application and data may be useful for them. And the other one is to be able to map the cloud height. So now we're studying like more into the 3rd dimension. So cloud height information can be extracted from thermal infrared data that we use to generate a pseudo 3-dimensional oblique image of major storm events. For example, actually nowadays when you watch the news, you often be able to see some like a weather model like this, but they appear to be like 3-dimensional, like you can see the cloud's thickness in it. So this example mapping is Hurricane Andrew in 1992. But the message over here is it is possible to, for certain application, to extract cloud height or thickness. And then there are also some other data for weather application. For example, the TRMM visible infrared scanner provides information of cloud type, cloud top temperature, using a 5-channel cross-track radiometer. So you can search online, but 5-channel, my guess would be probably like 3 visible band, near infrared and thermal infrared, could be. And then the Terra MISR sensor, they use the visible and near infrared. And Terra clouds and Earth radiant energy system is used to monitor the entire solar spectrum. Okay, so much longer spectrum measurement. So these are some other data sets for this type of application. And there are also some application for water vapor mapping. So it is important because water vapor is essential for precipitation. And also it is the most important greenhouse gas in the atmosphere. And also the formation of weather play an important role in the formation of weather process. So it is possible to map water vapor by sensing in water vapor absorption band. Several wavelengths can be used, but one of the most common one is centered around 6.7 UM. So a couple of examples, for example, METEOSAT1 used first water vapor measurement, the one launched in 1978, using the 6.7 UM region, and satellite generation 4 use water vapor bands in 5.1 to 7.1. So it also covered that area. And GOES use the water vapor band, which is from 6.5 to 7.0. So it's kind of also covered that 6.7 UM area. So these are the type of sensors that are sensitive for water vapor. There are sensors used near infrared for water vapor mapping, which is around 890 to 990 UM. 3 major water absorption bands will be one with the very strong absorption band centered around 942, and then a weaker absorption band centered around 906 and 977 nanometer. And MALDI's data set, for example, will have some bands that are sensitive to water vapor, which is band 17, 890 to 920. So that is still within this range. And band 18 will be 931 to 941. So it's close to this range over here. And band 19 is 915 to 965. So it's kind of close to this area over here. Okay, so typically they probably use that atmospheric window to pick these regions. And then the other subject related to water mapping is snow. So a lot of times, especially people who study the North Pole and South Pole, the glacier and water and ice and snow, this different formation of water is very important. And those kind of studies are often associated with the global warming or seawater level rise, because a lot of time people have a hypothesis, if we have global warming effect and you melt how much amount of the ice in the poles area, and then there will be certain water level rise, and that can cause significant flooding issue. So there are a lot of researchers studying those phenomena, so they concern about the snow mapping. So spring runoff can be both beneficial and disastrous, like especially those mountain area that depends on the snow or the water absorbed that is melted from the snow or glacier. And it's often very useful for agriculture purpose and also for potable drinking water, and it's often cause flood and avalanche hazard. And snow in the visible spectrum, so in the visible spectrum, they appear brighter than the vegetation, soil, and water nearby. So So you might be able to, for example, through certain band to use threshold to be able to separate them. However, sometimes if there are clouds in the data set, cloud also show bright. So if you only using the visible band, then there may be a challenge to separate between snow and cloud. So, so one of the strategies is to use these kind of multi-temporal images in relatively short time. For example, using AVHRR or ghost image, because these kind of weather sensor satellites are typically sampled in much higher temporal resolution. So in order to solve this differentiation between clouds and snow, is that clouds are typically constantly move. So when you find an image at different time, your ice will likely stay, but your clouds are likely move in the next image. So you can use this strategy to solve that issue. And the other one is often to use the middle infrared sensor to map the snow. And then again, one of the most common ground feature that is similar to snow are clouds. So here there is an experiment showing the spectrum for both snow and cloud. As you can see that in the visible light range over here, both features shows very high reflectance values, which means in the single band image, they appear to be quite bright, but they're both bright, so it's kind of difficult to separate them. However, when you go to the longer threshold, because of the significant absorption issue, the water in the snow will cause significant absorption, therefore much lower energy observed in that area. So if you have sensor who are able to provide data set in this kind of range area, then that difference can be significant in the image, because then your clouds will show much brighter and snow will show much darker color. So combine this, then you're able to separate the confusion. So therefore, through the visible and near-infrared portions of the spectrum clouds and snow reflect approximately equal amount of radiant flux. Okay, but in the so that's the meaning of it. In the near infrared, however, one cloud will be much higher and the snow will be much lower. Okay. So for example, when you work with Landsat TM, that would be the band 5 with around 1.55 to 1.75. So that's the middle infrared portion. And spot image band 4 also have middle infrared band. Okay. So this is basically means that if you study, try to map, extract the snow area using this image, you can use the visible band area to extract those bright feature, kind of whitish feature from image, and then use the one in the middle infrared to remove those, separate clouds and snow from your previously extracted sections. So that's why often you will be helpful to integrate visual band and the middle infrared. So there will be another application to map snow in middle infrared and microwave region. For example, from Landsat TM, there is a normalized different snow index. We like to use algorithm to map different type of index because it's very useful. You can convert image into just a new layer, just index. So in this case, you can also, using Landsat TM, you can also generate the snow index, which is using band 2 and band 5 in this equation. So so optimum threshold can vary from the NDSI derived image to another. One of the example in this paper over here, they use 0.7 as a threshold. Okay, so that's if you want to use it to map the snow. And also there's another equation used. If you use MODIS data set, you can use this equation to use this normalized difference snow index. Okay, but using MODIS data set, using the band 4 versus band 6. Okay. So again, often in this kind of equation, what you use is the S-sensor reflectance, which means that if you use the data set that is, with a value of integer type, you may need to convert it back, do radiometry correction and then convert that to the S-sensor reflectance, often also doing the atmospheric correction. Convert it back into the decimal point, the float point type of data set, and then calculate this index. Okay, so that's what this S-sensor reflectance means. So a lot of index.
So the difference between the one in the formula and this one, the difference, the S-sensor.
It's just sensor difference. When you use Landsat, you use band 2 and band 5. Okay. And when you use MODIS, you use the band 4 and band 6. So another one is to map snow from in the microwave region. So we're using a microwave data set. The microwave region of the spectrum offers promise for retrieving important snow information. So note here, they can provide some additional information. For example, the depth, the amount or presence of liquid water in the snowpack, and also discriminate snow versus glacier, dry versus wet snow. So these are some really, like some of the challenging area for snow related or glacier related study, because for example, snow versus glacier. So glacier is basically those like all year round pretty much stay as snow or ice, but the snow typically refers to those like seasonal, that in the winter time they may have some snow and then they accumulate over there. In the summertime they're going to be melt, and those, so a lot of time for those people who study how to monitor the change of glacier due to, for example, global warming or glacial melting or something. So they need to map the extent. And for that application, they need to separate the normal snow with glacier. So similarly, dry versus wet snow, okay? And also be able to provide snow water equivalent information. So it's kind of like modeling to predict, to assess how much, what is the area and what is the depth, and therefore the volume of the snow, and then be able to, if that melt into water, how much will be the equivalent water amount. So use that information for possible prediction of how much of sea level rise, right? So that is one application. And also, because microwave is active sensor, so it's not impacted by clouds. So that those are the advantages. So this is example using the ERS satellite centered around, so it's microwave data set centered around C-band, around 5.7 cm. So this image basically shows sea ice breaking off Alaska, okay, the offshore of the Alaska, okay. So that is the example of how the radar image of this will study these kind of snow, and then how can we separate it from other features.